forgot to record. So we shall study the processes where work is converted into heat and vice versa. In winter, when we rub our palms together, we feel warmer. Here, work is done by rubbing, and it produces heat. So as we know, friction between the surface of our two palms, they produce heat. And conversely, in a steam engine, the heat of the steam is used to do useful work in moving the pistons, which in turn rotate the wheels of the train. So obviously we're going to be discussing about heat, and these are just some introductory part to the chapter. It is the different applications of heat and things like that, um, caloric picture of heat, etc., etc. So I think we can go to the first topic of this chapter, which is I believe it's thermal equilibrium, if I'm not mistaken. Yes. So what is thermal equilibrium? I'm not sure if you guys have done equilibrium in chemistry, but when you hear the word equilibrium, what comes to mind? Anyone? So so far, okay, maybe you guys don't know, but equilibrium uh, in physics means that the forces acting on a system are zero, or they cancel out. The net force on a system is zero. In chemistry, we have seen that equilibrium means that any observable change is you can't notice any observable change in the uh, system. Like for example, if we have a reaction, for example, a chemical reaction, it attains equilibrium when the rates of the forward and backward chemical or forward and backward reactions are the same. So basically, what we can summarize it as is a stable state where no drastic, changes are happening to the system or to the object or to energy changes or forces, etc. Um, so as it says here, equilibrium in mechanics means that the net external force and torque on a system is zero. So force and torque, as we've already, studied, torque is, I guess you could say, the rotational counterpart of force. And I mean, force is pretty self-explanatory. It is an external push, we can say. It is the product of mass and acceleration. You guys know all that. So the term equilibrium in thermodynamics appears um, in a different context. We say that the state of a system is an equilibrium state if the macroscopic variables. Here, what does macroscopic mean? Anyone? Does anyone know the meaning of macroscopic? So, okay, so the macroscopic is what we can say. We can say it is the opposite of microscopic. So those are those variables. Macroscopic variables are those which are not involved in, very minute molecular transfer, etc. Macroscopic variables can be such as, pressure, temperature, volume. I mean, if you guys have studied the ideal gas equations, PV is equal to nRT. So number of moles, volume, pressure, temperature, etc., etc. These are macroscopic variables because they're observable by the naked eye, and they deal with a large amount of things. It's not very very small. Um, Although there are attractions and stuff between molecules and everything, but anyway. So we say the state of a system is an equilibrium state if the macroscopic variables that characterize the system do not change in time. What does that mean? That the macroscopic variables such as pressure, temperature, and volume are constant at that equilibrium state. And there's no, like I said, there's no drastic net change in the system or its surroundings. Um, so, for example, a gas inside a closed, rigid container, completely insulated from its surroundings with fixed values of pressure, volume, temperature, mass, and composition. Like I said, these are the macroscopic variables. uh, that do not change with time is in a state of thermodynamic equilibrium. So here we're given two diagrams, system A and B, two gases separated by an adiabatic wall. So what does an adiabatic wall mean? An adiabatic wall is one where heat energy is not allowed to flow. It is an insulating wall, which means we'll come to adiabatic processes and things like that as well. It is a barrier which does not allow the flow of heat to surroundings or anywhere else. So it's an insulation, I guess you could say. So if we look at figure A here, um, figure A, this figure has system A and B, two gases separated by an adiabatic wall. This is the adiabatic wall right here, this one. And so it is an insulating wall, so no heat is flowing from here or here. There's no heat flowing from A to B or B to A. So the same systems A and B are separated by a dithermic wall, which is the opposite of a adiabatic wall. A dithermic wall, since it contains the word thermal, means that it conducts heat. So heat is being conducted through A and B in figure B. In this case, thermal equilibrium is attained. So what is thermal equilibrium in this case? When the temperature, pressure, volume, etc. of A and B are equal, it will be said, the A and B will be said to be in thermal equilibrium. So moving on, these are again very rudimentary, topics. They're very basic topics. This is the base of the lesson. Um, Macroscopic variables you should know about because those are what we're going to be dealing with in thermodynamics. Thermodynamics is a macroscopic chapter. It doesn't really deal with intermolecular forces, anything like that. It deals more with, like I said, bigger variables which can be observed with the eye. So as it says here, in general, whether or not a system is in a state of equilibrium depends on the surroundings and the nature of the wall that separates them from the surroundings. So as we saw, the adiabatic wall um, means that there is no, what do we can say, transfer of heat, and the conductive wall means the transfer of heat is there, and thermal equilibrium will be obtained when there is no net drastic change between the two. So moving on, I see. I see my voice is breaking. Is it better now? I'm not exactly sure. Okay, it's better now? Okay, my apologies. Is there anything you would like me to repeat where you didn't hear me or anything like that? Okay. So again, we're just before we get deep into the chapter, I just want to make it clear we're just going to be going through NCRT today. And I'm pretty sure we won't be able to complete the chapter today because we're short on time. So I will at least try to get to the different thermal processes like isothermal, isobaric, isochoric, adiabatic, etc. So again, we'll be going through NCRT, the theory part, and if you guys would like, we can conduct another class later, whether you guys can inform me when, um, to complete the chapter. So as we know, we have, in general, whether or not a system is in a state of equilibrium depends on the surroundings and the nature of the wall that separates them, separates systems from the surroundings. Consider two gases A and B occupying two different containers. We know experimentally that pressure and volume of a given mass of gas can be chosen to be its two independent variables. So let the pressure and volume be PAVA in the two containers A and B, respectively. Suppose that the first two systems are put in proximity but are separated by an adiabatic wall. So this is just explaining the two cases we had up here, where we were discussing the figures about adiabatic and um, the conducting wall. So if the two systems A and B, as we saw above, are separated by an adiabatic wall, uh, the system is insulated from the rest of the surroundings, also by similar adiabatic walls. The situation, as we saw, is shown above. In this case, it is found that any possible pair of values, PAVA, will be in equilibrium with any possible pair of values, PBVB. Why? Because since they are, insulated and there is no transfer of heat or any values, PAVA under any condition will not change because there is nothing entering or leaving the system because it is insulated, and there is also a barrier of matter because obviously there are walls. Walls will block any extra matter trying to come inside. So for any possible pair of PAVA pressure and volume variables or values for those variables, there will always they will always be in equilibrium because the two systems are not interacting with each other. Therefore, there is no net change in either of the systems. Therefore, they will always be in equilibrium. Next, suppose that an adiabatic wall is replaced by a diathermic wall. Like we saw, it was a conducting wall that allows heat energy to flow from one system to the other. So it is then found that the macroscopic variables of the systems A and B change spontaneously until both systems attain equilibrium state. So what does spontaneously mean? Spontaneous means we can say it is a fast reaction, one which is irreversible. We will study about reversible and irreversible reactions as we, progress in this chapter. But it means that it is a fast reaction. Spontaneous means it's explosive. Well, not literally explosive, like it won't blow up, but explosive means it's, like I said, very quick reaction. So yes, exactly, kind of a sudden reaction, exactly, for Afra. So where was I? Sorry. So the macroscopic variables of systems A and B change spontaneously until both systems attain equilibrium states. After this, there is no change in their states, obviously, because they're at equilibrium. The situation is shown in the second figure, figure 12.1b, as I showed. You guys can refer to the what do you call it, to your textbooks if you have them, your NCRT textbooks. So the pressure and volume variables of the two gases change to the final pressure, which we can denote as PB dash, VB dash, and PA dash, VA dash, such that the new states of A and B are in equilibrium with each other. There's a star here. I would like to know what it says. If we go now, I think it should be at the bottom of the page. Yeah, so both variables need not change. It depends on constraints. For instance, if the gases are in containers of fixed volume, only pressures of the gases would change only pressures of the gases would change to achieve thermal equilibrium. So there are certain constraints that do govern the change of pressure and volume, which we will study later. We'll study about there are two processes, isobaric and isochoric, where pressure and volume are constant. Isobaric means you guys must have studied about bar, which is a unit of pressure. So in isobaric processes, pressure is constant. In isochoric process, volume is constant. So there are certain constraints, etc., etc. We'll get to that later. So now we come to the second topic, which is the zeroth law of thermodynamics. And I know it sounds a little funny, but this is, I guess, it is a law which will be used a lot in this chapter. So simply put, it means that, Zeroth law of thermodynamics states two systems in thermal equilibrium with the third system separately are in thermal equilibrium with each other. So let's try to understand this a little more. Let's read what they have to say. Imagine two systems A and B separated by an adiabatic wall, which means there is no transfer of heat between the two, while each is in contact with a third system C via a conducting wall. The states of the system, i.e. their macroscopic variables, will change until both A and B come to a thermal equilibrium with C. After this is achieved, suppose that the adiabatic wall between A and B is replaced by a conducting wall and C is insulated from A and B by an adiabatic wall. It is found that states of an A and B change no further. They're found to be in thermal equilibrium. So what this essentially means is that if we look at this system here, this is the adiabatic wall, yes? And this right here is a conducting wall. So while the adiabatic wall stops movement from here to here of heat energy and change in variables, what this separate system C does is when we have both A and B in contact with C. So what happens is when A is in contact with C, there's heat and energy transfer between this wall, and A and C attain equilibrium. Once A and C have attained equilibrium, then B and C also attain equilibrium until all three of these systems have the same equilibrium state. Because since C is in contact with both A and B, A and B's, we can say physical state or the state variables and the macroscopic variables, both of their macroscopic variables need to change such that both of them are in a thermal equilibrium with C. And since both of them are in a thermal equilibrium with C, they're also in a thermal equilibrium with each other. I mean, I guess you can use a mathematical analogy of this. If we say like A, let's represent as variables of A is VA of A is equal to variables of C, which is VA of C, and VA of B is equal to VA of C. Therefore, since both of these are equal, that means VA of A will be equal to VA of B. If we look at it mathematically, this is just an analogy. Obviously, it doesn't work like this, but that means the variables of A are equal to variables of C. Variables of B are equal to variables of C. Therefore, variables of A are equal to variables of B. And this is because obviously these are in thermal equilibrium. This is in an equilibrium state. So I guess you could use that to understand this better. So that's what the zeroth law states. If there are two systems in a thermal equilibrium with the third system separately, and they are in a thermal equilibrium with the third system, then they're also in a thermal equilibrium with each other, as we have seen here. So I guess you could say what the adiabatic wall does to stop thermal equilibrium between, or stop transfer of energy, the energy just, instead of going straight from here, it goes to C and then it goes to B, or they both go to C. So this is, I guess you could say, a bridge between the two, so that between A and B, which surpasses the adiabatic wall, that it forms equilibrium between the three systems. So now moving on, we saw this law of this. In fact, it's actually explained here. If TA, which is temperature, they took temperature in this case. This term, okay, so let's do this. The zeroth law clearly suggests that when two systems are A and B are in thermal equilibrium, there must be a physical quantity that has to be the same, that has the same value for both. This thermodynamic variable, whose value is equal for the two systems in thermal equilibrium, is called temperature. So this is another thing I would like to touch on is thermal equilibrium is usually decided by temperature. So if temperature of two systems is equal, it is said that they have attained thermal equilibrium. So in A and B, like I used all the variables, but like we saw, temperature of A is equal to temperature of C, and temperature of B is equal to temperature of C. So that will imply that temperature of A is equal to temperature of B. Similar to what I used with just the variables. Instead of using just temperature, I used all the variables. So again, this is just explaining the zeroth law. So again, so this is the zeroth law. We'll move on now. Oh my God. My apologies. My computer is lagging a little bit. I'm not able to scroll properly. So now we come to the other topic, which is heat, internal energy, and work. So these are the constituents that will form, I guess you can say, the first law of thermodynamics. So before we continue, I'd like to hear, what do you guys know about heat, internal energy, and work? What do you understand by this? Because I've been talking a lot, but I would like to know from our audience. Anyone can answer. You guys can type in chat or use your mic, whatever, however you feel comfortable. Okay, I guess never mind. I guess I'll just explain it. So heat is pretty obvious. Everyone knows what heat is. Heat energy is an energy that is, first of all, we'll talk about it. It's a dissipative energy. So when heat is, yes, these are collectively referred to as thermodynamic state variables. So looks like you have quite the grasp on this. So we'll get to state variables, what they mean, um, in a second. But for now, let's just talk about what they are. So the heat, yeah, that's fine, no problem. So obviously, heat is I mean, it's pretty self-explanatory. It's heat. You touch something, it feels hot. It's a type of energy. Internal energy, we can say, is the energy due to all of the different forces and interactions between system, the different constituents of the system inside, well, a system, obviously. So internal energy is the total energy of a system that is isolated from the surroundings with no net energy on it. And it is by virtue of things like, intermolecular attractions, pressure, volume, etc., etc. Work, we already know. SI unit joule, it is very obvious. So, for work, while we know what it actually means, work in thermodynamics has a slightly different uh, definition, or its formula is slightly different. So let's see what they have said here. The Zeroth Law of Thermodynamics led us to the concept of temperature that agrees with our common sense notion, obviously. Temperature is a marker of the hotness of a body. It is what we use to measure the degree of heat. That's why it's called degree, I guess. You could say we use excuse me. We use it to measure the degree of heat, how hot something is, the hotness of a body, as they have determined or described here, determines the direction of flow of heat where when two bodies are placed in thermal contact. Thermal contact means they are placed in contact with each other either by radiation, convection, or conduction, where there's a transfer of heat energy from one to the other. I'm pretty sure you guys must have learned about radiation, convection, conduction. That's pretty obvious. Radiation, if you guys want me to go through that again, conduction is when heat transfers through physical contact between two systems. So that's like when you place, your cooking pot or whatever on the stove directly. If you have a stove and heat is or fire is directly touching your stove, the heat energy is transferred through the metal to your pot. Convection is by virtue of, as we've seen, a cyclic motion through different mediums. So that's like, how we've seen that hot water rises up, cold water comes down to take its place. There's a cycle. Radiation is like sun. So that is energy is radiated through vacuum or a medium. Um, and that's how we get energy from the sun. So these are three basic types of energy transfer. So anyway, when two bodies are placed in thermal contact, heat flows from the body at higher temperature to the one at lower temperature. Obviously, even when we put like, let's say a hot, like for example, you have, I don't know why anyone would do this, but if you have coffee, you put it in the freezer, or you have room temperature water, you put it in the freezer. Why does it get cold? The reason is the water loses its heat to the surroundings, which is the temperature of the fridge, and the heat moves from the higher temperature of water to the lower temperature of the fridge. So just remember that heat flows from a higher temperature to the lower temperature. The flow stops when the temperature is equalized. That's why that's another, again, that's where thermal equilibrium comes in. One way to measure thermal equilibrium is that the temperatures of two systems should be equal. That means that they may be in thermal equilibrium. Also, this meeting will end in 10 minutes, so I would request you to rejoin. So yeah, we'll continue, and if it ends in the between, you guys can rejoin if you would like. So the flow stops when temperatures equalize. The two bodies are then in thermal equilibrium. We saw in some detail how to construct temperature scales to assign temperatures to different bodies, as we've seen, conversion from Kelvin to Fahrenheit, Kelvin to Celsius, Celsius to Fahrenheit, etc., etc. We now describe the concepts of heat and other relevant quantities like internal energy and work. So the concept of internal energy of a system is not difficult to understand, obviously. We know that every bulk system consists of a large number of molecules. Internal energy is simply the sum of the kinetic energies and potential energies of these molecules. Like I said, the total energy of a system inside it by virtue of intermolecular interactions and the potential and kinetic energies is the internal energy. We'll see ahead, an ideal gas or an ideal system usually doesn't have potential energy. because there's no attraction between its molecules, and therefore we usually don't deal with that. So we usually don't consider potential energy. But obviously, in real life, we don't have an ideal system. Therefore, kinetic energies and potential energies summed up can be seen as the total internal energy of a system. So we remarked earlier that in thermodynamics, the kinetic energy of a system is, as a whole, is not relevant. Internal energy is thus the sum of molecular kinetic energy and potential energies in the frame of reference relative to which the center of mass of the system is at rest. So thus it includes only the disordered energy associated with the random motion of molecules. So kinetic energy, as we know, molecules are in complete random motion, especially in gases. Usually in this chapter, we will be dealing with gases in thermodynamics, especially in physics, and we will be dealing with ideal gases. That's again why I said there's usually not much potential energy, because one of the postulates of an ideal gas is that there's no attraction between its molecules. So therefore, there's no potential energy. But we'll get to that. So the internal energy is thus a sum of molecular, kinetic, and potential energy in the frame of reference relative to which the center of mass of the system is at rest, which means the mass shouldn't, the center of mass, as we've studied in rotation, shouldn't be moving, because if the system is moving, there's going to be extra kinetic energy due to that as well, etc., things like that. So we denote the internal energy of a system by U. So though we have invoked the molecular picture to understand the meaning of internal energy, as far as thermodynamics is concerned, U is simply a macroscopic variable of the system. So as Afra was saying, she actually typed to me that heat, internal energy, and work are referred to as state variables. What do state variables mean? Would any of you like to make a guess or have any previous understanding? I'd like to hear from you guys. Uh, Close. Of course, no. Basically, what happens is Afra. Okay, for the rest of you, Afra messaged that they directly affect the thermodynamic state of the system. So yes, but that's any variable. Any variable change, the thermodynamic state of a system changes. So what a state variable actually means that its value depends only on the state of the given system. So what it means is, let's say we have a thermodynamic system and it goes through a certain process, which we will learn about later, which is like adiabatic or whatever. So this thermodynamic system goes from state A to state B, for example. And what a state variable means is that the internal energy or the change in internal energy only depends on it only depends on the difference between state A and state B. So state variables only depend on the two different states, I guess you could say, not the path taken. So there are certain, we can say variables. They're called path functions. They depend on which particular process or which way that a thermodynamic system has gone from path A to or state A to state B. And then there are state functions. They don't care. You could have done a loop-de-loop and drawn all kinds of squiggly lines and put it through 700 different processes just to get it to state B. But the state variables will only depend on the final state and initial state. So it's somewhat, I guess you could say, obviously I'm not the greatest at explaining this. I think we should refer to NCRT. But what it basically means is that the state variables do not depend on a path taken from point A to point B. They only depend on point A and point B itself. So internal energy of a system is an example of thermodynamic state variable. Its value depends only on the given state of the system, not on the history, or in essence, it says not on the path taken to arrive at that state. So thus the internal energy of a given mass of gas depends on its state described by specific values of pressure, volume, and temperature. It does not depend on how the state of gas came about. Like I said, it doesn't matter what path it took or what happened in the intermediate between state A and B. It only depends on yeah. So the definite values attained in state A and B, as Afra said, she messaged again. She said, as in definite values attained, right? So yes. So the definite values of state B and definite values of state A. So state variable only depends on, for example, if we take internal energy, change in internal energy, for example. We put a thermodynamics system through a change or a process, and the change in internal energy will be only the internal energy at B, state B, and internal energy at state A, and the difference will be um, the difference in internal energy. It will not depend on how it got, because what happens is certain variables, there's certain loss of certain variables through the state or through the path. So those are called path functions or path variables. There's loss or gain or change in those variables, and it depends on how the path is taken. So a longer path will result in more change in the variables. So in state variables, there's not that the path doesn't really matter. So it does not depend on how the state of the gas came about. Pressure, volume, temperature, and internal energy uh, are thermodynamic state variables. If we neglect the small intermolecular forces in a gas, the internal energy of a gas is just a sum of the kinetic energy and kinetic energies of its molecules. Like I said, uh, we will be neglecting the potential energy formed due to the attraction between the molecules of a gas, because we will be dealing with an ideal gas. So like I had said, the internal energy is just the sum of the kinetic energies of the excuse me, of the we can say of the molecules of a gas. So sorry, one second. What were we talking about? We're talking about the internal energy. Yes. So it is just, so the internal energy of the gas is just the sum of the kinetic energies. Just bear with me here. My computer is lagging. I don't know why. Kinetic energies associated with various random motions of its molecules. As we know, in a gas, molecules are in random motion. It has no definite volume and no definite which we learned before. Obviously, gases do have volume, but it's very negligible if left in free space. They take the volume and the shape of the the container or the room or whatever they're put in. So associated with the various random motions of its molecules. We will see in the next chapter that in the gas, this motion is not only translational, motion from one point to another in the volume of the container, it also includes rotational and vibrational motion of the molecules. This we will study in kinetic theory of gases, which we can do after this um, chapter if you guys would like. That's also very important compared to thermodynamics. We have things like degrees of freedom, etc., and the different. It's more of a microscopic chapter. It deals with the motion of different molecules and atoms of a gas, etc. So now we come to what are the ways of changing internal energy in the